Okay, so I reviewed the live session we had. Gosh, you guys, nobody said anything about the quadratic formula. Okay, I wasn't paying attention when I was writing, so ignore that. Uh, so what I'm going to do instead is just summarize what we did in the live session here, um, just so you have the notes from that. Um, yeah, so let's take a look here. So we took a look at a summary so far, right? And then we took a look at a sample solution, or a example, I should say. And so we'll work out the example solution. And then the last thing we did was probably the most important for the live session, and that was we did some graphing solutions. And we also started characterizing the origin, that is, in terms of its stability. And that's because it is our systems are autonomous differential equations, and so the origin is always an equilibrium solution for the system, right? So if I have x prime equals AB CD times x, if you put in x equals 0, right, x prime is equal to the 0 vector then, and so that means that it's always an equilibrium solution. Okay, good. So let's go ahead and get that summary going here. All right, so we have x1 prime equals ax1 plus bx2. x2 prime equals cx1 plus dx2. And we said that that was equivalent to writing the system as x prime of t equals a, b, c, d times x. And you might see it also abbreviated as x prime equals a times x. And so this matrix A in this case is this a, b, c, d. Good. So I will try to write it out in terms of its components as we go. Alright, so then we said that our ansatz is x of t equals e to the lambda t times v. And so if you differentiate that, the only thing with t is the exponential function there. You would just have e to the lambda t times v. And so on the other side of that, you have a, b, c, d times x, and that would be a, b, c, d times e to the lambda t times v. And so if you set these two things equal to each other, we see that we get our system of equations. Lambda and v must solve the system of equations a minus lambda v1 plus b v2 equals 0, and c v1 plus d minus lambda v2 equals 0. And this is the system of equations that you want to remember. Alright, so how are we going to solve this system of equations? Well, notice that v1 equals v2 equals 0 is always a solution. Okay, so are there any non-zero solutions? Because we need v1 and v2 to not be equal to 0. And so in order to get non-zero solutions to this, we must have an infinite number of solutions, right? Why is that? Because there's only three choices, right? When you're solving a system of equations, there is either a unique solution, which it could be, right? Because we have 0 as one solution. Excuse me. There's either no solution, and that's not this case, or there's an infinite number of solutions. And so if we don't want the zero solution as the only solution, then that means that we must have an infinite number of solutions. And in order to get an infinite number of solutions, that means that the two equations must actually be the same equation. And the only way that that's going to happen is if the determinant of the matrix of coefficients is equal to 0. Excuse me. So that means that if you write down what this is, gosh darn it, the lambda okay, so that means that we have, if you write this out, you'll see that you get this. And we're saying that this, you can use the shortcut that this is the trace of A. So the trace of A, the trace of the matrix, is the sum of the diagonal values. Okay, and then the other thing that's over here is the determinant of A. Okay, and so as a shortcut then, if we're given, x prime equals A, B, C, D, this is your matrix A here, times x, then you can go to the shortcut that the eigenvalues are coming from lambda squared minus the trace of A times lambda plus the determinant of A equals 0. Now I should say this is only valid, only true when A is 2 by 2. Okay, and that's because for a 2 by 2 you get a quadratic. If this was a 3 by 3 matrix, you would actually have a third order or third degree polynomial in lambda. Okay, and so this is only good for the quadratic case. Good, and now let's see if I can remember the quadratic formula this time. Gosh, that's embarrassing. The quadratic formula is the trace of A plus or minus the square root of the trace of A squared minus 4 times the determinant. Yeah, I was messing around. My hair was flying around. I've got the corona or pandemic hair, meaning I haven't been to the barber in a long time. Okay. I gotta get down there. Okay, so that's my those are my solutions. And so we call this the discriminant, the thing under the radical sign. So the discriminant is equal to the trace of A squared minus 4 times the determinant of A. And so we said that if the discriminant is positive, that leads us to two solutions are real. And then we have to go back to our system of equations and solve for V1 and V2. And actually, we could solve that symbolically right now. So suppose that we've got lambda equals lambda 1. Then we've got our system A minus lambda 1 times V1 plus B times V2 equals 0. And now if we've done everything right, we don't need the second equation because it's a constant multiple of the first. So I could stop here and just say, well, this is the equation that I need to solve. Right? And so I need to choose a V1 and V2 that are not constant multiples of that. So I should say that the full solution to this is a line, right? But we just need a V1 and V2 that's on the line. And so we're just going to take V, and what I'm going to do is I'm going to flip the coefficients around here, these two things, and I'm going to put B first and A minus lambda 1 second, and then I'm just going to negate one of them. And I usually negate the second one, but that's just an arbitrary choice. And so there's your eigenvector corresponding to lambda equals lambda 1. And so I'll put a V1 there. So notice that this is a vector with a 1. This is a scalar value with a, this one's a scalar value with a V1. Good. And so similarly, you could find V2, right? So for lambda equals lambda 2, you could actually write down, well, let's just go ahead and do it. Now you don't have to memorize this. Please don't memorize this. But the technique is what I want you to remember. So this is going to be b and a minus lambda 2. Good. So there's your two eigenvectors. Okay. I probably shouldn't have shown you that. Okay. Don't memorize that, please, because that would be a waste of brain space. Okay, so this is your full solution right there. Okay, so we have two other cases that we're going to be going through this week. The complex case and the case of a single repeated root for the eigenvectors. Good. So in the next video, we'll continue and we're going to solve that. Where are we in our stuff that we looked at? We've done our summary so far. Next we'll do our example solution, and I'll see if I can't get, I don't think it'll take that long, so we'll probably get into the graphing in that video as well. See you then.